goal of this module is to build a photorealistic 3D renderer line by line from scratch, coding every single line that you see here, and the end result is this image that will be rendered out. First, we're going to install Python. So Google search Python, go to Downloads, and then download the appropriate version for your system. Windows, Mac, other platforms such as Linux, Ubuntu. Next, download Conda, whether Anaconda or Miniconda. So I'm going to Google search Conda, go to download Conda, and you'll see there's Anaconda or Miniconda. Anaconda comes pre-installed with packages for the scientific packages, such as NumPy and such. Basically, since we're making virtual environments, we're going to choose which ones we want. So we want the minimal package to download, so we're going to use Miniconda. Click on that, and you choose the one that's appropriate for your system, Windows, Mac, Linux. Going to download Mamba, so Google search Mamba.org. And this is the one, the fast cross-platform package manager, the GitHub. So you could see in here that one of the easiest way is to install Conda first, and then you use this command line to install Mamba. So we'll do that later on. After you've downloaded and installed Python and Conda, you should be able to go to your command line or terminal and type in Python -- version, and it should tell you what version of Python. You should be 3 or above, 3.8 or 3.9 and above. And also for Conda, if you do Conda -- version, you'll see that you have a version of Conda. Next, we're going to install Mamba, and we're going to do it through Conda. So if you put in this line, Conda, that's a Conda command, I'm going to say install Mamba, which is basically like a faster version of Conda for production. -N is for name, base. C is going to be where it's going to look for it, and it's going to look for it Conda Forge. If you do that, I already have it installed, but if you do that, it will get the information and install it for you. In this case, I have it installed, but you should see that yours would be installing if you don't have Mamba already installed. Going to create Python virtual environments so we don't mess up the installation of our packages and our base system, so it could stay isolated. We're going to use Conda, or basically Mamba, which is a faster version of Conda, to manage the package, the virtual environment, the packages there. And Mamba is compatible with Conda. So how you create basically a virtual environment is you do Mamba create, or you can replace Mamba with Conda if you don't have that Mamba installed. Do -N for the name of the environment, and then we'll call it PYRT for Python Raytracer. And right after that, we could say the packages we want to install. So we could say Python, and if we do not put a version, we could say, for example, version 3.9. If you want a specific version, equals 3.9. For any package, you could say the exact version if it's available on the repository. If we don't put a version, it's going to take the latest version. So for this, we're going to need Python, Pillow, and NumPy. And if you press enter, it's going to install these. And it's going to ask if you want to continue. And you're going to say Y for yes. And it's going to install everything. And it's going to say this is what's going to change. You say Y, say yes. And just wait for everything to install. And you could see here it says Conda. You can replace that with Mamba in a lot of cases, and it will still work to activate the environment. You're going to activate the virtual environment we just created. So it says here Conda activate PYRT, that would work, but you could also replace that with Mamba, faster version. So Mamba activate PYRT, press enter, and now you'll see that we'll have in brackets PYRT, so we're in that virtual environment. And if we do Mamba list, it will show you what packages are installed in this virtual environment. So we installed NumPy, and we also did Pillow, and a version of Python, which is 3.96, which is newer than the version that's on my base system. Another package we're going to install is Jupyterlab. We could have installed it when we created the virtual environment, but want to show you how you can install packages after a virtual environment is created. So we're going to Google Jupyter, that's Jupyter with a Y, lab, one word. Go to the project homepage. You scroll down, you see install Jupyterlab, and you could install it with Mamba install. That's where it will find it, the repository, and then Jupyterlab. So if we're going to copy that, and if we go in here, we could paste that in, or type it in, Mamba install -c Conda Forge Jupyter with a Y lab, and then press enter, and it's going to install everything in that virtual environment. One thing using Mamba, it would be faster to install than using Conda, but you could use Conda instead and it will work as well. And you could press Y here to confirm. So it's installing. And it's done installing here. And we could check by typing Mamba list. And you'll see if I scroll up, this lists the packages that are installed in the virtual environment, and we'll see Jupyterlab's installed. Now we can enter Jupyterlab, but to do so, you want to make sure of two things. You want to make sure you're in the folder on your file system where it's going to be the root of Jupyterlab. So for example, here on Windows, it's going to be my E/code folder, which you see in here. So right now it's empty, but when I create files, it's going to go in here. The other thing, you want to make sure you're in the virtual environment because that's where we installed everything. So how do you enter and exit a virtual environment? So if you're in here, you do Mamba or Conda. Remember, Conda is the original, Mamba is the faster version that we installed. So if we do Mamba deactivate, if you're already in the virtual environment, it's going to take you back into the base environment with basically your base system with your original installation of Python and everything. To go back into the virtual environment, you say Mamba or Conda if you don't have Mamba installed and you're only using Conda. Say Mamba activate, and the name of the virtual environment, which we created, is PYRT. Press enter. And to start Jupyter Notebook, well, actually, this is Jupyterlab, the newer version of Jupyter Notebook. We're going to say Jupyter with a Y lab, a space between the lab. Even though the name is Jupyterlab one word, when we actually activate it, we say Jupyter space, then lab, and press enter. It's going to start a web server with this address, and which is the root is going to be this folder here, and it opens up in your web browser over here. And then we could create the different files, the console, the terminal, markdown files, Python files in here. To exit this, what you would do to shut it down, to stop the server inside your terminal, you press Control-C if you're on a Windows. It might be Command-C, or it might be the Control-C on a Mac, and should be Control-C on Linux as well. You might have to do it a couple of times, and it will actually shut it down. And you'll see here that you're back into your terminal. Let's start setting up our code. So I'm going to enter Jupyterlab again. It's going to start up a web server, which you'll see here in your browser. And we're at the root. This root here again corresponds to the folder that you started Jupyterlab in your terminal or your command line here. So for this, we're going to create a notebook, which allows you to basically write code and a narrative at the same time. So it's basically like as if you're writing like a documented code, and it's easier to share and explain and make slides or HTML or PDFs afterwards. So we're going to say this is the Python 3 kernel. So we'll click on this. And first we're going to change the name up here for what we want. Here we're going to call it, well, you can name it here. Click on it. You can press F2 or right click and choose rename. And I'll call this Raytrace. And in here we'll have cells. The cell could be either code, which actually is code that will be executed, markdown, which is actually text, or raw. So the first one in here, we're going to set up our structure first and then fill it up with code. So I'm going to put it in markdown. And markdown, some of the language you could do like header. And in this case, I'm going to basically give it a name. I'll put one header with a pound or hashtag there. Say Raytrace. And if you press Control Enter, it's going to render that out. To make a new cell, you can press a plus button here. And I'm going to change it from code to markdown again. And then I'm going to basically put text under here to explain what's going to happen. So say, let's code a photorealistic 3D renderer. And then you could hold Control and Enter, and it will render that out. So one thing why I'm using this platform here is because that normally in pre-production, before production in code, or when you're doing research, you're basically exploring and you're not really going through all the software engineering of production, of linting, unit tests, documentation, and all that. So this allows you to prototype really quickly, or basically get you a proof of concept really quickly and basically present it to other people, and before you go in and actually do the proper software engineering practices. So to continue here, we could do plus, and we'll fill out all the sections first. So again, this is going to be markdown over here. And here will be our import. So I'll do 3. So this is going to be header 3 hashtags or 3 pounds there, and say imports. This will be where it imports. If I press Shift Enter, it's not only going to render that out, it's also going to make a new cell for me right under it. And after that, I wanted to make this markdown again. A shortcut to do this is if you press the escape key, then you could press M, and that would be the shortcut to change that to markdown. And then if you press Enter, it's going to accept that change, and now you can edit again. But it's now in markdown mode. If you want to change it back to code, you press Escape to switch modes, press Y on your keyboard, and then press Enter, and you'll see it's back to code, and then you can enter again. So I'll switch back to Markdown. So escape, M, enter, Markdown mode. I could type. So here, I'm gonna put dash, oh sorry, hash, space, classes. This will be the section for my classes. Press Shift Enter to render that and go to the next cell. Under classes, I know they're the classes that I'll need. So escape and enter to be in Markdown. In Markdown language, putting an underscore at first will make it an italic. So do vector class underscore and then press Shift Enter. That's going to be an italic. The next class I'm going to have here is going to be Shift M Enter underscore sphere class underscore Shift Enter. Right. Next one will be the Shift. Okay, I'm going to press Escape M Enter. I've been saying Shift M Enter. Sorry, it's Escape M Enter. So now I'm in Markdown. I can edit. I'll do underscore checkered sphere class and then press Shift Enter. All right, so that will be the subsections over here. What's good about that is that if you go into the table of contents, you could actually start seeing these things, and it will allow you to jump around in the notebook pretty quickly. And you could press this button, and you could even see the subtitles as well. So I could go for the classes, go to vector class, sphere class, back to the Raytracer at the top, or hide that. So if I go back to the folder, the file browser here, I'll have this mode, or this view again, or for my files over here. By the way, when I created this file, again, it actually creates it in my real folder there, because this is the root when we executed it in here when I started our server. So back to this, in this cell, the next thing will be functions. So escape and enter to be back in Markdown mode, or you could drop down and select Markdown mode. It will be 3 hashtags and then functions. Then Shift Enter. After functions, we'll have a section for initialize variables. So escape and enter, then 1, 2, 3, initialize variables, then Shift Enter. The next section will be escape and enter, and then it will be, well, first I'm going to put 3 hashes, then scene description, Shift Enter. And then there'll be calculations. So Markdown, I'll just do it from here this time. 3 calculations, Shift Enter. Then it will be Raytrace. So escape M enter, then 3 hashtag Raytrace. And in this section, I'm going to have the timer to show you how fast it could render, even in Python. Shift Enter here. And then we're going to have a section, so Shift M Enter. This is going to save image to file. Shift Enter. Keep saying Shift M Enter. I mean Escape M Enter, basically to change it into here. Shift Enter actually renders it out and go to the next cell. So here, Escape M Enter to go into Markdown mode, and then hashtag display image, and then press Control Enter, because I didn't do Shift Enter because Control Enter will render that out but not make a new cell over here. And I'm going to save it by pressing the save button here. You could also do Control S if you want to save it. All right, so we fill out the sections. So if we go into our table of contents, we'll see all our sections are here. Now it's time to actually implement each one. So under import, you can press the plus sign, or what you could also do, if I'm in here, if I press escape, again, this allows me to manipulate the cells in here. While I'm in escape, I can press D, the letter D twice, as in delta, and that will delete a cell. So be careful with that one, because you can't undo that, at least not that I'm aware of. If you want to add a cell after the one you're in, I'm in on this cell right now because it's highlighted right there. You can press escape, then press B, and it'll create a cell after it. To delete it, press escape, D. And if you want to create, let's say here, a cell before it, you press escape and press A, and you'll create a cell before that. Again, you could also right click and choose delete cells, and it'll tell you basically the shortcuts for some of the options here. So delete cell DD. So delete that. So going into the import, I'll just add a cell with this, pressing plus, and we're going to do our imports here. So one of them is from pill, import image, then from func tools, import reduce, import NumPy as MP, import time, and import numbers. The purpose of this notebook, or to go through this, is basically to get you a Raytracer, show you could code a Raytracer from scratch, and basically to show you these tools to see how prototyping or proof of concept would work. But to understand the details of what all the code will be, that will be in later videos. So to execute this code, first of all, notice that there's these square brackets here with blank in there. That means this cell have not been executed yet. And one other thing we could do is go to view and say show line numbers, so that'll make it easier to see the Python code. To execute the code, you could press this play button, and it will run the selected cell, which is this. And you'll see one, and if there's no errors, if there were errors, you'll see something show up here, or if there's output, you'll see something that show up under that cell. So nothing showed up because there were no errors, there were no output, and a number showed up here, so that means it ran and executed successfully for the imports. Next, we're going to start implementing classes. If you're going to do any type of like graphics, computer graphics, most likely you're going to implement the base functions or the base utilities, which would be like points, vectors, matrices, if you're not using a library. So here is no different. We're going to implement our own vector class. So we're going to put under here, I'm going to press plus, and I'm going to implement the vector class, but again, I'm not going to explain everything because the purpose of this video is to basically show how to use these tool sets to prototype our proof of concept and get a working photorealistic 3D render at the end of it. That's the main purpose. To understand everything will be in other videos. So the vector class. So it's a Python class, so we call it class with the convention, capital V or capital letter for the name of the class. Vector 3, we're importing the object and the destructor or the destructor-like function, the init underscore init will be self. We're just going to take in an X, the Y, and the Z. And it's going to set in here the self, basically the member variables, self X, self dot Y, self dot Z. So now this is going to be the properties, or basically the variables, the member variables of this class when you instantiate it. That's going to equal what's being brought in here, x, y, z, x, y, z. Okay. Next is we're going to define what underscore mul is, underscore. That'll be self, other meaning the other thing you're going to multiply with. So it's going to return a vec3 self x times other self dot y times other and self dot z times other. Then we're going to have def underscore add underscore self other. It's going to return vec3 self dot x plus other dot x, basically adding the components. Self dot y plus other dot y, self dot z plus other dot z. Then we're doing underscore sub to subtract self other, then return vec3 self dot x minus other dot x self dot y minus other dot y self dot z minus other dot z. All right. Now we're going to do the dot for the dot product. Self, and then we have other. So we're going to return self dot x times other dot x, and that's going to add, because that's what a dot product does. It multiplies with the individual components of the two vectors, and then add them all together to make a scalar or a single number. So self dot y times other dot y plus self dot z times other dot z. Then we have absolute here, underscore abs, underscore just self here, and it's going to return the self dot, which we'll implement in a second, meaning this is not implemented yet, the member variable or the member function, which is called a method. And then we're going to do the norm, so def norm self, so mag for magnitude, short for magnitude. Now we're using MP, again, that is from the NumPy package here. SQRT is square root of the absolute value of ourselves. Like basically we're working on ourselves here. It's like inline, and it's going to, well, not inline because it's going to actually return something, but it's going to work on itself here. So then we say return the self object here times 1 divided by NP where mag equals 0. So if this NP where, you could look it up on the NumPy documentation, but if this, how it works is if this is true, it's going to be this value, or else it's going to be this value. And that will close this, that closes that bracket there. All right. Then def components self return. This is returning the individual components x, y, z. So the member variable of x, of y, and z. And here we have extract self and oops here. So what this is going to return is the vec3 extract con of self extract from here cod of self y, the other one's .x, and extract cod and self .z. And this bracket closes that, and this closes this bracket. Okay. So the last thing we have to do here is def place self cod, and it'll be r vec capital V vec3 mp zeros. So NumPy arrays of zeros, so basically you pass in the shape that you want of that. So whatever shape this is, we're making a matching NumPy array that are filled with zeros that match this that shape that we brought in. So that's the first part of the vec3 that will be here. The next one would be same thing, np zeros, shape again, and the last one, same thing, np zeros, shape. All right, so then we'll do place rx cod self.x right there, p place r.y cod self.y, and then np place r.z cod here, cod, what is cond, I guess, self.z, then return r. And this finished the definition of the vector class. So let me just save that. We could execute it, but most likely it won't. But if there are errors, it probably won't find it at this stage because nothing's executing the values yet. So let's just see. Oh, it did find error. Line 6 here, and yeah, because I forgot to put a colon here. So let's control enter again. Okay, for now it didn't find any errors. We'll see if there's any calculation errors afterwards. Next, we're going to implement the sphere class. Remember to save your notebook along the way. It also is designed to autosave by default, I believe, every 2 minutes, in case you lose your notebook. So in here, I'm going to click on that cell. If you want, by the way, to collapse this cell, right next to the button, you could click on it, it will collapse, and you could just click on the 3 dots here, and it will open up the code again. So in the sphere class, make sure that cell is selected, press plus, it's a coding cell, and we're going to make a class sphere, inherits from object, the constructor or constructor like method or function, or class function here. It's going to be this, diffuse, mirror, okay, so that's how much the mirror effect will be there. And we're setting member variables for the object. All right. And put mirror, self mirror, assign it to the mirror that's passed in. Okay. So for here, now we're going to do the method or class function intersect. You have to pass in the self object, self, because it's class. And here, O and D. B. Again, for the math part, this is going to be explained in later videos. This is just to show you how it would all work, and basically at the end of it to get a working ray tracer. That's the goal of this. C is going to be the absolute value of the member variable C itself plus the absolute value of O that's passed in, capital O, minus 2 times the self.c, now the dot product of that, and self.r times self.r. Excellent. Then we have this b times, which is square, so b to the power of 2, so b squared minus 4 times c here. Then we have the square part of this. So using NumPy for the square root, find the maximum between this, the 0, and this value. Basically, like using like a clamp, that h0 minus b minus q. Then divide that by 2, then h1 equals same numerator except that you put a plus sign instead. Divide that by 2. And then you have h and p where, which we discussed before. If this condition is true, if h0 that we just define up there is above 0, that's actually in here, and h0 is less than h1, then we'll make the value of h0. If that's not true, then it's h1. The pred over here is disk 0 and h0. And at the end, what we're going to do is return from this function np where if pred, if this is true, then it's h, and if it's not, then it's far away. Which we have to define. Great, so that's the definition of that member function or method here. So now what we're going to do is diffuse color, which is just put an M. It's a lot easier as a function because all you do is just return self-diffuse. Then we have light self 0, O, capital D, small d, the scene, and the bounce. All right, so M is capital O, okay, capital O plus D times small d. Okay, that's M. N is equal to M minus self.c times 1 dot self.r. So here is going to be the intersection point. This is going to be the normal. Then we have, 2L, or basically the TO capital L means this is the variable is for the direction to the light, or to the light, or 2L. So L minus M dot norm, right? And the next one is to capital O, which is to the direction of the ray origin. So it's E minus M dot norm. And we have nudge here, which is equal to M plus N times a really small number. We'll say 0.0001. And M is basically, so it avoids itself. So M avoids itself. That's really what it is. And again, this may not look like it makes sense now, but after going through and understanding what each piece means, and we build this up one by one, coming back to this will make a lot more sense, seeing these algorithms. Right now, we're just implementing it to get a working ray tracer here. So now what we're going to do is basically the shadow part. So we're going to find the point if it's shadowed or not, right? And the amount to finding out is if M can see the light. If it could see the light over here. So how that's going to be done is we have light distances as a variable here. And we're going to do some list comprehension, which is S intersect, right, with the nudged value to L, or to the light here, for S in scene. So basically cycling through all the scenes, which we haven't defined yet, but we will go through all the scenes and then intersect with it. And then we'll get the light distances for all of them in a list. Then we're going to find the nearest, so light nearest. So reduce, which we imported up here from functools. So we have reduced, and P minimum, and then light distances, like that. And then can it see the light? We'll make a variable see light. And we're going to again do light distances. Well, basically this variable. Well, I'll still type it up. Distances. Right, so remember this is a list. We made list comprehension here. So we're going to say scene.index of, well, the self, find its own index. And if that equals light nearest. So basically what this does is going to go through it and see if it equals the light nearest. Then if it's true, that means to see the light. If not, then it's false. Right? So now we're going to calculate the ambient. So that is color equals RGB, which we will define. So two things, like RGB here, if you notice, we did not pass it in and it wasn't defined in this scope. And also, there's another one that in the other method here, intersect, there's far away, which was never defined in the scope and was not passed in as argument variables. The reason why, what you can do in Python, if you define these as global outside of a class or a function scope, it will be seen in here. So same thing with RGB. If you're wondering where that's coming from, it will be defined later when we get to the section like initialize variables. We're just utilizing a feature that's in Python, where you could define global variables and they're accessible inside afterwards in other scopes of class functions or methods here. So back to RGB here, 0. So it's three values for our red, green, blue, 0.05, 0.05, 0.05. So that's the ambient. So Lambert shading basically is just the diffuse, right? So no specular or anything like that. How you calculate that? So make a variable LV, MP the maximum. So N dot, right, which is the normal, dot 2L. Remember, 2L is the direction of the light, and 0, right? And then we just basically sum it up with the color that's there. So self dot diffuse color M times LV times C light. So this is the algorithm. The diffuse color over here, the maximum between the dot product of the normal and direction of the light. And do you see the light? And that gets added to the current color. All right, so now let's deal with reflections. So if we have a bounce of less than 2, so basically when a ray hits a surface, that counts as a bounce. So if we have that bounce less than 2 here, so then the ray D, again, this is going to be an algorithm that we explain later on. Dot norm. Right? So then we have the answer of that is going to be the color you append to it, add to it. The ray trace, which we haven't defined yet, we will define this. Nudged. And then ray D, scene, bounce, +1. And we're looking at the mirror, which when we initialize the sphere, we entered a mirror value that has been set as a member variable, which we are now accessing over here. Great. So now this part here is going to be the blend Phong shader, basically the shading part. Blend and Phong shading, which basically means the specular. So when over here, this was the ambient. This was the ambient. This is the Lambert shading, basically the diffuse shading. We calculated the reflection, and now we're calculating the specular. So we're going to do Phong and dot, and in here is TOL. Again, that is TOL is the direction to the light plus TO, capital O there, and that is the direction to the ray origin dot norm of that. And now we add it to the color for the calculation, which would be, again, the same RGB that's going to be defined in the initialized variables globally. RGB 1, 1, 1 times NP to the power. So basically every element that's inside here will be to the power of the value at next to it, right? So NP clip Phong 0 to 1. Basically, clip is like clamping, so it's making it between 0 and 1. So if the original value of that array was, lower value was, let's say, negative 1.2, since that's lower to 0, it's going to be clamped to 0, so it's going to be changed to 0. And if there's a number that's higher than 1, like 2.3, it's going to be clamped at 1. So this makes it stay within that range. And then all that 50. Remember the power there. So clamp it, then put it to the power of 50. And then we check each element we're broadcasting. That's what you could do with NumPy. Every element with that value C light. So, and then at the end, you return the color. So you bring in the light, we calculate all these things, then we get the ambient. We put that to the base color. Then from here, we get the diffuse. We calculate the diffuse and add that diffuse, make that contribution because we're adding it onto that ambient color. So now we have the ambient with the diffuse, and then we have the bounciers for the reflection. We calculate it, and to the same color we're adding onto it. So now we have the ambient, diffuse, and the reflection. And here we're calculating the specularity. So we're adding on top of that. So ambient added with the diffuse, added with the reflection, and now added with the specular. And then we've returned the color for this. And that is the spheres class right here. Okay, so we did the sphere class. Next, we want to do the checkered sphere class. So since we're using object-oriented programming here, since we're using classes, we could just inherit from the sphere class and add extra features to this. So from here, select that cell, press the plus sign. So we're going to have a class, checkered sphere. And who we're inheriting from this sphere class. So this is going to be a child, and the parent is the sphere class. So basically, it inherits all this automatically. And then we could just add our extra function here, or member function, also known as a method. So it's going to have all this, inherit that, plus this new one, this new method, new function, self m. So we're calculating checker here, which would be m.x times 2. We're going to cast this as type integer, and then we're going to do the mod or modulus or modulo of this. So basically, every even number would be 0. Because that's what this says, the mod. And then from here, for the z, that was for the x component. Now for the z component, again, this times 2 dot as type integer again, mod 2. All right. And then what we do is just return self dot diffuse times checker. And that is the checkered class. So we define all our classes. I could collapse these so we could see it. So all our classes are defined. We could see them here. The table content, show that. Classes, we could jump to them, just check them out. Click the 3 dots to expand them again. We're just going to check to see if there's any quick errors in the classes, so I'm going to execute this again. Okay, so no errors, at least not yet, but there's no calculations yet, so there still might be some errors or typos or logical errors. Click here. Okay, so there's an error, unmatched closing bracket on line 10. Remember to show lines, go to view, show lines. So line 10. Let's see. That opens that opens this. So for the intersect, this here, okay. That is supposed to be like this. So let me save that. And let me execute that again by clicking here. Okay, so at least it executed. So at least there aren't any typos. There could possibly still be some logical errors, but we'll see that later. And here, click here. All right, so this seems like it's okay. I'll explain a little bit of this just really quickly, even though the purpose of this is really just to get a working Raytracer photorealistic 3D renderer and not really go through every algorithm, just to show over here is instance basically checks that variable and checks if it is that type. If it's true, then it returns it. If not, then it does NP extract. So Conda is short for condition. How NP extract, this is a NumPy function that if this condition is met, then X over here is actually like an array or an ND array, I guess you could say for here. And if any of the conditions are met for any of those elements, those specific elements will be returned. So if some of them are false, they will not be returned. So you're just extracting what passes here. Just as a side reference, if you want to know the functions used in NumPy, you go into Google, type in NumPy Documentation. And you could click the documentation here, and then you could choose which version of NumPy that you're using or you want to see. The latest one right now is 1.21. Most likely that's the version we have if we didn't specify one. It's possible it could be an older one if we install dependencies and it doesn't work with the latest one. It could reinstall an older version using Conda or Mamba. So you click on here. You have all these things like what is NumPy, but for example, right here, we want to know like what is tile. We type in tile, the NumPy tile. When we use NumPy, we said import NumPy as NP. So you could go in here and it will explain what that is. You go in here and check repeat, for example. And then you could look at NumPy repeat and explain how to use it. All right, so now we're going to write the code for the heart of this whole render engine, which is the Raytracer function. So while we have this cell selected, we're still making another. We're in the function section because we are making another function. We're going to press plus, and we're going to define a Raytrace. It's going to take big O, big D, a scene, and bounce. And this is going to be a value that's already there, a default value of 0. So O, just quick definition, O is the ray origin, D is the normalized ray direction. So basically it's the magnitude is going to be a unit vector over here, and bounce is how many times the number of bounces starting from 0, basically starting at 0 for camera rays over here. And the scene, as you'll see later, is basically in the scene description, the scene that we're going to pass in, I'm going to do the ray tracing on. And in this case, if you notice, we just made spheres, so the scene, sphere class and a checkered sphere class, so the scene is just going to consist of spheres right now in this simple example or prototype code. All right, so let's calculate ray tracing. So we have the distances equals here, list comprehension again. So s.intersect, we used this earlier, putting big O and big D, again, the origin of the ray with the normalized ray direction, right? For S in scene. Basically, we're going in scene, cycling through them, and basically checking the origin of the ray origin and the normalized distance, and to see if they're intersect. If it's true, we put them then. If it's false, we put it in here. So we know what's true and what's false in here. Then from here, nearest equals reduce, which we brought in from functools, reduce. And what reduce does here, we're going to take the NP minimum and the distances. From that, we're going to take the color. We're going to create a new color, RGB, assign it, initialize it at 0 over here. Now we're going to cycle through. We have this tuple, sorry, that there, from that we're zip, from scene and distances. Here. So just a quick explanation, reduce is basically going to apply this function to every element in that list here. And this initializes the color, RGB, and zip. What it's going to do, we have two pretty much lists like array type things that have the same element number. They basically going to pair them up. That's what zip will do. And then you have the two values out here. Now, next thing what we're going to do over here, after we do the zip, we're going to check if there's a hit. So if the nearest, that up here, does not equal far away. Again, we used far away earlier. We're mentioning that somewhere. I can't find it at the moment. Far away was the first time. We use it up here. And again, where we're getting this, it's going to be globally defined in the initialized variables. So even though you're inside the scope of here, it's going to see it. So if it's far away, it's not far away, and D over here. What is D? This D we got from that over here is equal to nearest. Then we have a hit, right? So if np.any, so in our list of hit, if any of them are true, at least one of them in this list or in this array type thing, then we do this, right? And what we do is we have DC here. We're just doing some extract calculations, which I'm not going to go for the explanation of the algorithms. That will be explained later. Oh, we're going to extract here. Extract hit. Extract that out of that. Scene and bounce. All right. So once we calculate all these, then we could put it onto the color because it's hit. So the color with nothing, and then all these things were hit, then we adding to that color place where the hit is. Awesome. So, but if we go through all this and there's no hit, then none of that gets updated. But at the end, it's just going to just be the color. If there's no hit, at the end you're going to return basically the color. So if there's a hit, you do all these calculations and the color is returned. If not, the color is already defined and it'll just be returned here. All right, let's just check this. All right, so a code block executed. Okay, so we define our functions. Now we're going to the initialize variables. So now some of those variables that we've been seeing, like far away and RGB, we're going to define in here. So let's click here for that cell, press plus, and basically let's start with RGB. So RGB is actually a vec3, right? It's just an alias. In fact, we could have used vec3 instead of RGB here. So it's basically taking up all these properties. So we're using RGB just because it has very similar properties that we use for a vector, but we're using it for color. And for basically keep it intuitive, the variable name will be RGB, so we just assign it to that there. So that defines that. We want to know the screen size, so we'll define that. So W will be the width, H, it's in a tuple over here, H for the height. And in this case, we'll say 400 by 300. That will be the resolution of our screen or our final image. And we need to know where the point light position is, the light is. So the light is going to be defined as a vec3. That's why we created these classes and functions, so we can start using them here. We'll just call light L, capital L, and it will be a vec3. From the vec3 class, we're creating an object from that class. And remember, the vec3 takes an x, y, and z from the vec3. So here, we're going to say 5, 5, minus 10. That's where it's going to be in the world. The I position, we'll call it E for I. That is also a position in vec3. So vec3, where is it? Where are we looking at in the scene? Or looking from the scene? 0, 0.35, and -1. That's I position. And the other thing going to the far away. So far away. We want this as a really small number, like really small. So it's like 1.0 e to the 39. Well, really, sorry, not really small, really big. It will be negative if it's really small. So that's like 1 times 10 to the power of 39. So imagine how far that is. And those are our initialized variables. So now those other variables that you see in these scopes, we'll use it. And it's aware of it. Let me just execute this cell. So it's aware. Okay, let me save that. All right, so now we're going to do the scene description. Basically, what that's going to be is defining what's inside our scene. So far, we only created spheres. And what it's going to take is the center, which is going to end up being a vector 3. And the diffuse, well, R as well here. That's going to be a value, like a scalar. And diffuse, which is also a vector 3, but it's a color. So we say it's an RGB because we define that. And then if something's mirror, like the mirror value, like how much it reflects, if we don't put anything, it's going to default to 0.5. So let's start defining our scene. So under scene description, select the cell, press plus. It's a code mode over here. So we're going to say the scene, which gets passed in, for example, into the Raytrace where we pass in the scene. It's going to be a list, just a regular like Python list. And inside it, we're going to have our objects, which are, we'll start off with a regular sphere. We're going to create an object from the sphere class here, right? So first one will be a sphere. And you, at the end, you could go and start making your own scene description, create them in different locations, and see what they give you. 3, and we could say 0.75, 0.1, and just 1 here. Okay, so that's, again, if we look at sphere, sphere right here. That's the center. And then we're going to need a scalar, then an RGB value. So that's the first argument. Now we need a value, 0.6, that's for the R. And now we need a color, which is a vec3, but we created RGB. Remember, we define RGB to be the same as a vec3. But when we see RGB, we at least know it's meant for color. 0, 0, 1, like that. All right, so that's our first object in our scene. Let's add another object in our scene. So I'll put a comma. It's going to be a sphere again. Vec3 for the center of it. This time I'm going to put it negative 0.75. It's going to be 0.1. Then 2.25. So for the XYZ position for the center. Great. Values for the R is also going to be 6.6. And when we're talking about sphere, if you're wondering, this is the center. R is going to be the radius of the sphere. So that's the radius. This is the center, the vec3. And next, we're going to do the color of that, RGB. 0.5, 0.223, 0.5. And sphere, vec3, minus 2.75, 0.1, 3.5. Then we have 0.6 here, an RGB, 1.572 for the color, 0.184. All right, so we define 3 spheres. Their centers are at different locations. They all have the same radius. And what are we going to do here? Then over here we have different colors. I'm going to add, instead of a sphere into our scene description, we're going to do the checkered sphere. So bring that in. And the values here will be like this. So we do that. I think that's 5.50. So yeah, this is a really far away number, negative, but then right, and then you put at 0 here. Then we're going to do the radius though, the positive version of that. And why we're doing this? Because this is going to have checkered on it, so it's going to look like the floor. So it's just a big sphere that's really, really big, but it's so big that it's kind of like the Earth. It looks, from our viewpoint, it's going to look like a flat surface. Then RGB. And again, we're making it really, really small, like really, really far away. A big number, but it's 0.5 for negative for the center. But then over here is going to be positive for the radius. So that means it's just a little bit of an offset, but it's going to be so big that it's going to look flat with the check, and we're going to use that as a floor. That's this. That is not 0. That's here. And now we have RGB, 0.75, 0.75 for the color, and 0.75. And this time, unlike this one, we're going to use, so again, checkered sphere is inherited from sphere class. It's a child of it. Sphere class, when you bring it in, you're bringing it in, even though it's one value here, it's actually a vector, so is XYZ, the radius, the diffuse color RGB, which is really a vector. But then we didn't pass in the fourth argument, which is mirror because it had a default value here. But this time we're actually, for the checkered sphere, we're going to be using that. And we're going to put it 0.25. And that defines the scene description. Let's see, press Control Enter or press the play button to execute and look like it's fine. So we'll just save that. And that went to an X. So just to show you, if I press a button here, you have that black circle. That means there's a change that has not been saved. So you see the change has not been saved. If I press the save button, it goes away. So I know it's saved. Okay, so we initialize our variables. We did the scene description. We have our functions, our classes made. So let's do some calculations here. So click on the calculation section, press add. What are we going to do here? So we have R, which we're going to class a float of the W, which is a width, divided by H right here. So now we have screen coordinates. Screen coordinates x0. So the screen coordinates is going to be x0, then x1. Sorry, x0, then y0, then x1, y1. So we have this here, S. It's going to have -1 to 1 divided by R. Remember, W width, H is height. So ratio, right? So 1 divided by the ratio. 1 divided by R, right? Plus 0.25. So remember, PEMDAS, this is going to happen first, then it's going to add that. Then 1, -1 divided by R plus 0.25. So x0, for the comma, x0, y0 over here. Actually, -1, 1, 1, 2, 3, 4. Yeah. So x0, y0, x1 here, first comma, then y1. Then we have x is equal to np tile. So basically, tiling is going to take that and repeat the pattern. So np from NumPy, right? And then inside there's going to be linspace. And it's linspace is going to like linear interpolate between these values. So we have s, this s, first element of it, to the s, third element, remember it's base 0, then width, and then the height. So that's just going to keep tiling that. And then we have the y, which is going to repeat. And you could look these up in the NumPy documentation, what these functions mean. So in here, we have np.lin space s. Now it's 1 s 3 h w. So now let's just execute this cell. Control enter. Okay, we got a number, no errors. Okay, so we're going to Raytrace section. Click on the cell, press the plus button. We're in code mode here. So we also say with render time. So we're going to use the time that we imported here to measure how long it takes to render. So t0, we're going to say time.time. So we're going to save the start time here, t0, t0. Q is going to be a vec3. We're going to say x, y, 0. Again, x and y were calculated from here. This is x, this is x, this is y. the color, we're going to call function Raytrace and give these in. So Raytrace. So we have E Q minus E dot norm scene, and we're going to print took. So that's how long it took. Time. Time t 0. So we're calculating the time of when it stopped. We're recalculating the time, subtracting from when we initially took the time, and in between we actually did the render and put everything in the color, and then we print it out. Let's just execute this. Actually, no. I'm not going to execute. Actually, no, I can't execute. Everything else has been executed, so let's see. Oh, just looking at this attribute error following the stack, it's calling X, which that's that call up here, which is calling Raytrace, which is this function. And then, oh, there's a problem with the distance here. Distance is calling S intersect. Intersect is, let's see, S intersect. Okay, distance as well here. Okay, intersect, yeah. Then absolute. I could see this is an O, and that's a 0. Okay, so line 10 in the intersect function. Or not function, well, it is a function, but member function. So let me go to that, line 10. So intersect, we are in sphere, line 10. That's big O, that's not a 0, that should be an O, big O. Let's see if that fixes the problem. Let's save that. I'm going to have to execute this cell again. So actually, to make sure, what I'm going to do is clear this whole thing. Go to kernel, clear all it, and restart. So it's going kernel, kernel and restart, and clear all outputs. So it's starting from scratch again. So I'm going to execute that. Just keeping pressing play until there's an error. Execute. Execute the functions. Initialize the variables, scene description, calculations. All right, so now we're back to here. Let's see if there's a problem. Okay, seems to be another problem. RGB not defined. Well, I said RGB, but I see here is RBG. So a name error, line 43 in the fung. Okay, so if where we're defining the fung, that should be in here somewhere, the fung. Yeah, so not RBG, it's RGB. So where am I? RGB. This is under sphere, under the light method, or the member function. That was a typo. That shouldn't be RBG, should be RGB. So save. Again, go to kernel, restart, and clear all outputs. So say yes, clear everything. So what you could do, if you put, okay, I'm going to calculate this, but you could do it up to here, but I'm going to select this cell and go run, should be all above selected cell. So everything above here will run up until this point. So all above selected cell and run. Everything is calculated, no errors. and I can tell it's calculated because the numbers are there. All right, so let's see if there's any more errors with the ray trace. Click here, press. Oh, okay. It went through. It said it took 0.1729 seconds. And this is Python. So that's pretty fast for a scene, a resolution of 400 by 300. I remember how long it used to take the early days of computer graphics. So we want to be able to save this file and display it. Okay, so now let's save the file. Select that cell, press plus. So to save the file, we'll give it a file name. So I'll just put that in a variable. And I'll call it rendered scene.png. All right, so we're going to have to put this in a usable format, and we're going to be using pill since it already has implementation of saving out to common image formats. So we're going to be using image from the pill or the pillow that we installed module earlier with Mamba. So we're going to return an RGB. We're going to do a list comprehension. So we say image.from array. And what do we put in here? So it's 255 times and clip. So C, which we'll define in this list comprehension, 0, 1. So we're clipping, remember it's clamping. So anything below 0 will be clamped to 0. Anything above 1 will be clamped to 1. Gotta take that, reshape it to height and width. Okay, 2, 3. All right. I'm going to convert that type, everything that's calculated, into NumPy have types built into them as well, part of their the packages modules there. So uint8, which is unsigned int 8 bits there. And then we do L. And this is all common for pill or pillow. For C, remember we use this C, where we're getting that in our list comprehension. We're going to be cycling through in the color that we got here, right? It'll be color, all the components, like XYZ. And then we put in well, XYZ is RGB, so red, green, blue. We put in the red, green, blue components there. So now that we have that, we could actually go and use from the image module from pill image dot merge, and we say what type it is. It's going to be an RGB image. I did it again. RGB image, and what we're passing in this. So that creates. This is going to create the object of it. We took that. We merge all those components together into one, and then we're going to say save. And where do we save it to? That file. And if we did everything correctly, we select this. I'll save first. Run the cell. It's going to save this image. And if I press refresh, I went back to the file save over here. It created an image over here. And you can see the server still running. That image got created. Now we're going to actually, you could double click it. You can see it in here, or you can click in there and you'll be able to see it, but I'm going to show you how to display it into the notebook as well. Let me just save this. So we're done. Now we're just going to display. This is specific for, this code is going to be specific for the Jupyter notebook. So outside of it, probably not going to do anything in regular Python. So if we select this, and do a plus, make a new cell that's for code. There's this, if you go in from python.display, import display, and then execute that. So now we could use display and we could show images inside here. And how you do that, we create a new cell. We're going to use display that we just imported. So we say display. And what are we displaying? Well, again, we're going to use from pill here, the image, a function that's from there. So image dot open. And what is it? This file name that's been already defined and we already executed, so it holds that and it knows where we are locally, so it's going to open the local file which we saved there. So save that, and now if I execute that, Control Enter, it actually shows us the scene that we just coded from scratch and render it out and then save to an image right here. So if we look at this, remember, so all these classes, the vectors, the vector class here is the base, the foundation here for calculation. Then we have the sphere class, which are the objects we have in our scene. We only have sphere in here. And this ground is actually a really big sphere, really, really big. So let's look at the scene description again section. So remember, we made 3 spheres, right? 1, 2, and 3. We have 1, 2, and 3 spheres. We set the colors, and all 3 of them have the same radius. So that's why these 3 look the same. And then we have a 4th sphere. Remember, checkered sphere. So that checkered sphere so we have the sphere class, and then we made another class, the checkered sphere class, which derived from here. And this creates the checkered pattern. But when we created it in our scene over here, remember that we made the radius really big. Or the radius is really big here, and the center point is really far away, but it's the same size as the radius, just a little bit lower. That's a distance that is lower than this, right? So because it's really, really, really big, it looks flat from this viewpoint where we place, when we're building the scene, we're replacing the initialized variables, we're placing the eye, replace where the eye is, replace where the light would be, and this is going to be the resolution of the image here, 400. 400, so the width is 400, the height is 300. And you could probably tell from the colors RGB, so red, green, blue, so 001. This first one is blue. I can tell from the RGB, 0 for red, 0 for green, 1 for blue, so that's that. That's the one we define here. This one, probably the purple. You could probably look by here. Well, XYZ. Well, you could tell by the Z depth too. This is the closest one. This is the purple's the next one. And then you have the yellow. And then under it's a checkerboard, which acts like a ground plane. And remember that we set the level of specularity and set the level of reflection as well. So that's a ray tracer from scratch, writing every line of code in front of you. One reason why we use Jupyterlab or notebooks or the Jupyter notebooks here is that once this prototype is done, this proof of concept, what you could do, well, you could save it and you could go to file and then export the notebook as like HTML, LaTeX, Markdown, or PDF, or actual executable like Python code. It will just comment out these things and it'll be executable. Minus like extra things like that won't be affected in a real Python script. This is the display specifically in the Jupyter notebook world over here. So it's very useful in terms of like once you have these, this serves as a document to explain what's happening with actual working code. and you could use as an example to actually go in and software engineer this in a proper software development cycle. And when you do export it, just a note, when you're doing, why you're doing it in HTML or as reveal.js slides, you could do like kind of like a deck or kind of like a PowerPoint kind of thing or presentation. PDF is very useful because at least not everyone have to have, let's say, a Word document like Microsoft Word. Not everyone has that installed. PDF is kind of universal. Anyone could download a reader. One thing though is if you try to export it as that, if you're on Windows, for example, it's going to say that it can't do it because it needs something installed. You need to install, for Windows, Mictex. So if we go into Google here and go, well, to this website, you type in mictex.org, click on it. You could go in, download, and choose the one. So on Windows, you'll choose the one for Windows. You download it, install it. Once you install it, you're going to have to open it up. So you'll find it once you have it installed on Windows. In the Start menu, look up Mictex and then choose Mictex console. Choose the one that's appropriate. And choose administrator over here. Choose administrator mode here. Pops up. Then probably the first time you want to go to updates, check for updates, and then update them all. Once you have that, make sure you close. You probably have to restart Mictex console. You probably have to restart Jupyter Lab. So you have to close that. And the other thing is you're going to probably have to include this path to your system path. So in your system properties here, we're going to go to advanced, go to environment variable, and you choose your path, and you add this path to your environment variable. You save it. You might have to restart the computer. A lot of times nowadays, you don't necessarily have to do that, but you probably have to restart Mictex, and you might have to shut down your server for right here. Right now we're running Jupyterlab. Make sure I save it. What I'm going to do is go to shut this down to show you how we could print this out. So to shut it down, it's running right now. It's live. It's running with the dot over there. So if we select it, the notebook for what we wrote, go to File, Close and Shut Down Notebook. There's also Control-Shift-Q on Windows. Are you sure you want to shut down? Say yes. Okay. And you see the dot is no longer next to it, so it's not running. And you'll get this screen again. So this notebook is shut down, but the server is still running. So to shut down the server from the terminal or the command line that is open, press Control-C. You might have to do it a few times to shut it down. So now it's shut down. If I were to go back in here, you'll get this message, server connection error. This won't work. You can't start it up. Even if I try double clicking on it. Nothing, because the server is not on. So once you have that shut down, you could exit this if you want. Then you could restart again Jupyterlab. Once you have my Mictex installed, Jupyterlab install, start up the server again. And now it should pick up the environment path. I could double click on my, not seeing the Jupyter Notebook. It will start running. You get that dot to show that it's running. It still saves what you've done, so I'm not going to recalculate it. Now I want to export it. I could File, Export Notebook. I'm going to do it HTML, so I'll do that first. So I choose HTML, I'll name it, say save. It's going to export it. It doesn't really tell me that it's done, but I could see in my home folder that it's here, right? So I go back, I don't need that tab, I'll close that. I'll also export it as PDF, but again, I already set up my PDF. And it's going to ask me to save it. It may take a few seconds before it's generated, but now, again, I have mine already set up. If you're doing this for the first time, at least on Windows, you're probably going to get an error until you install Mictex and set up, like I mentioned, install it, update, make sure you install all the updates, then add that path to the environment path, save it, close everything, reopen everything, and now it should be able to do this. You save that out. And now that's done. So to view it, they're saved out here. So I could drag and drop, let's say, the HTML here. Oh, well, not in here. Let me make a new tab, drag and drop the HTML. So here's the same notebook, but it's static. So now you can present this to someone else or send it, but not everyone wants to open the HTML. You could also export out as JS slides. Well, let me have this running, double click on it. It's export out as JS slides, but reveal.js slides, and you would have to know how to use that format to get that as kind of like a deck or PowerPoint type presentation. Also, Jupyterlab is designed to read these type of formats. So if you click on the HTML, it will actually read it directly in here. And the PDF as well, it would read it directly in here as well. So it's really meant to be a way to consolidate all your formats. You could even open the .png file in here to view it. But so why, if we're able to do that, why did we put it in here? It's so we can make a document and present it to other people as well. So once that's done, you have a presentation, you have a tool set, a tool suite here, and a workflow here that could do prototypes, basically proof of concepts, test out algorithms with actual text and a narrative to understand what's going on, with basically code examples with results. Once that's approved, or you get the point across, then you could actually go in and actually code your project correctly. Now that you're done, how do you close everything up? So you go to all your notebooks that you have open. You could go to File, Close and Shut Down Notebook. And say, yes, I'm shutting it down. So the notebook is not running. So you're good with that. You could close this. However, the server, the console or the command line that is running your Jupyterlab, you want to shut that down. So click in it and press Control-C or possibly Command-C on a Mac, or Control-C. You might have to do it twice to interrupt it the first time. A lot of times it doesn't stop it. And now I'm out of it. Again, if you want to go back in, make sure you're in the folder, navigate to the folder where your the notebooks will be, or where you want to open Jupyterlab. Type in Jupyterlab. It's going to start the server again. It should automatically open up the website. If not, you click on one of the links on your local host. It will load it. You're back in. Your files are there because I opened it here. I could double click the notebook and they're back and I'm working in. Just going to show one other thing here. So back in here, we're going to go back into our environment. So Mamba activate PYRT and start Jupyterlab. Going to start up the server. Brings us up. So I'm going to take this notebook. I'm going to duplicate it just because I want to keep the original. And you could press F2 to rename it. I'll just call it 2. just want to show you here. I can close that. Well, one, I could take the kernel, reset the kernel, and clear all outputs. Say restart. Everything's clear. For the scene description, I want to move them around. So if we look at our picture here, if I open that, you have them over here. So one of the things I want to do is change the colors. Let's start with that. So first, the output file, I'm going to change it. I'll just call it scene 2. That will be the output file. And in the scene description, let's first just change colors. Let's do, the first one is RGB, so it's blue. So let's make it red first. So it's from 0 to 1, 1 being 100% of that color. So it's going to be 100% red, 0 green, 0 blue. So that means it's going to be red. Here I'm going to make it green. So 0, 1, 0. So 100 red, 0 red, 100 green, 0 blue. And this one's going to be blue. So 0, 0, 1. Everything else will stay the same. Let's save this. And what I'm going to do is just run the entire thing. So run all cells. So it's just going to go through everything and generate the image. And you could see it did it in basically 0.2 seconds. So as you saw here, in my scene description, I changed the colors. It's going to be red, then it's green, then it's blue. If I want to bring the blue vowel a little forward, what you could do over here. Actually, well, first let me just compare these two. So if we have the new one here, you could should be able to stack that so you could see next to each other. So this is the new one, blue, green, red, or red, green, blue, and this was the original. So you could close that. So we change a color. We could also change the position. So for example, here, this is the first line here is the center or the description of it. So right now, let's say the blue one, instead of 3.5, let's say 2.5. You look at where it is, that will move. So we go in here and choose run all cells. You see it moved a bit. This is the scene description. And this is how actual software works, whether you're working in Blender or Maya or 3ds Max or any other DCC, digital content creation software. What happens is what you do in the viewport describes the scene, and when you press render, it sends out a scene description like this, and the renderer renders this out. So if we go into Blender, for example, right here we have the scene, right? It basically describes when you're creating objects and you're modifying, you're basically describing the scene, kind of like what we're doing here. Of course, this is very simplified. We just have simple objects where we define the class, but every software, 3D software, works the same way, high level at least. If we go to the renderer, you see the render engine. Right now, Blender has Eevee, there's Workbench. Eevee is a GPU renderer, then there's Cycles, and then there's LuxCore. With this, you could actually build this out and actually make it a plugin and make it a renderer for Blender or for Maya or whatnot and hook them in. When you press the render button, which would be here and say render image in Blender here or render animation, it's actually going to go through, if it's an animated scene, go through step by step, or if it's a single image, when you say render image, is actually going to translate what's inside the scene into a scene description, like what we have here. So basically, if we're plug it into our render that we just wrote here, it would export it out into a scene description that this, in a format that it could understand, and then it would render out everything and give you the final image, kind of like what happens here. And things that would pass in are what are the objects in the scene, other things that we mentioned in here. Where's the light? Where's the eye or the camera? Right? What's the resolution or the width and the height of the image? That's what's happening when you do that over here. And you can understand that when you see there's new features in software like Maya or Blender, it's actually done by a lot of times by people who are actually working in production, and they find the things that are off the shelf in the software not doing what they need for that project, whether it's a video game, AAA game or independent game or a film, again, independent film or, a blockbuster film as well. Then you need to actually go in and code in the functionality you need for it, such as, let's say you're making your own renderer. And then you plug it into your actual software that everyone uses. That's how new features get picked up. So you can imagine if you're able to do these things and add features or functionality that you need for production, big companies will want you to be able to do that. And they'll be actually headhunting you to actually for jobs, and you don't have to be chasing them if you have this ability. Thank you for watching. Remember to like, comment, subscribe, and hit the notification bell.